Welcome to this video on solving LeetCode problem number 542, titled O1 matrix. In this problem, we're tasked with computing the distance to the nearest zero for each cell in a binary matrix. We'll explore the problem, break it down step by step, and discuss an efficient approach to solve it. Let's dive in. In this problem, we are given a binary matrix called mat that has dimensions mxn. Each cell in this matrix contains either A0 or A1. Our goal is to compute a new matrix, answer, of the same dimensions, where each cell in answer, ij, represents the shortest distance from that cell in the original matrix to the nearest cell containing A0. The distance between two adjacent cells in the matrix is defined as 1. For instance, if two cells are directly next to each other horizontally or vertically, the distance between them is exactly 1 step. This problem requires us to find the minimum distance for every cell in the input matrix while adhering to this definition of adjacency. Let's look at an example to clarify the task. Suppose the input matrix is a 3x3 grid, as shown here. The matrix mat contains 0s and 1s arranged like this. The first row is 0, 0, 0, the second row is 0, 1, 0, and the third row is 1, 1, 1. The output matrix, answer, should then be 0, 0, 0, 0, 1, 0, 1, 2, 1. The explanation for this output is that each 0 in the input stays as 0 in the output because it is already at a distance of 0 from itself. The cells with 1s, however, calculate their distances by finding the shortest path to any nearest 0. To further break down the example, consider the cell 1, 1 in the matrix, which has a value of 1. The closest 0 is just 1 step away, and we can move in any direction up, left, down, or right to reach it. Therefore, the output value for that cell is 1. Similarly, for the cell 2, 1, with a value of 1, the nearest 0 requires 2 steps to reach. For instance, we can move up to 1, 1, and then up again to 0, 1. This 2-step path determines the value 2 for that cell in the output matrix. Now, let's consider another example to ensure the concept is clear. In the second example, the input matrix mat is again a 3x3 grid, but this time, all rows are 0, 0, 0, except for the middle row, which is 0, 1, 0. The output matrix for this case is 0, 0, 0, 0, 1, 0, 0, 0, 0. Here, each 0 remains as 0, since no movement is required to reach the nearest 0. For the cell 1, 1, which has a value of 1, the nearest 0 is 1 step away in any direction, so the output value is 1. The problem also specifies constraints, such as matrix dimensions being as large as 10,000 elements in total, which means the solution must be efficient. Additionally, it's important to handle edge cases like matrices filled entirely with 0s or having only one 0 to ensure the solution works across all scenarios. To solve the 0-1 matrix problem, our goal is to calculate the shortest distance from each cell to the nearest 0. The challenge lies in doing this efficiently, especially when dealing with larger matrices. One method we might consider is the brute force approach, which uses a naive search strategy. Here's how it works. For every cell in the matrix, we calculate the distance to the nearest 0 by exploring the entire grid. This is typically done using either a breadth-first search, BFS, or depth-first search, DFS, from that cell. While this method is straightforward, it has significant drawbacks. Since we perform a BFS or DFS for each cell, the time complexity becomes O, m*n*, m plus n, where m and n are the dimensions of the matrix. This means the approach scales poorly for larger matrices. Additionally, there's a lot of redundant computation because many cells end up exploring the same regions repeatedly, making this approach inefficient in practice. A more efficient solution is the optimized multi-source BFS approach. Instead of treating each one as a starting point, we flip the perspective and treat every 0 as a source. The idea is to perform a BFS simultaneously from all 0s, propagating distances outward to neighboring cells. This ensures that each cell is processed only once. To implement this, we start by initializing a result matrix, where cells containing 0 are set to 0 and all other cells are initialized to infinity. Next, we place all 0 cells into a queue, which serves as our starting points. From there, we perform a BFS, updating the distances for neighboring 1s as we go. This approach processes the entire matrix in O, m*n, time, as each cell is visited exactly once. The space complexity is also O, m*n, accounting for the queue and result matrix. This method is not only efficient but it also avoids redundant computations, making it a practical choice for this problem. However, it does require additional memory for the queue. Another option is the dynamic programming approach, which uses a two-pass scanning technique to calculate distances. The intuition here is to leverage the relationship between a cell and its neighbors to find the shortest distance. In this method, we perform two sweeps over the matrix. First, we iterate from the top left to the bottom right, updating each cell's distance based on its top and left neighbors. Then, we perform a second pass from the bottom right to the top left, adjusting distances based on the bottom and right neighbors. The result matrix is initialized with infinity for all cells except 0s, which are set to 0. The time complexity remains O, m*n, as every cell is updated twice, once in each pass. Space complexity can be O1 if we modify the input matrix directly. This approach is efficient and memory-friendly, but it may feel less intuitive compared to BFS, especially for those unfamiliar with dynamic programming techniques. The strategy we've chosen to implement is the multi-source BFS approach. It strikes a balance between efficiency and clarity, making it well-suited for this problem. One of its key strengths is its simplicity. Propagating distances outward from 0s aligns naturally with the grid-based structure of the problem. It's also highly efficient, with a time complexity of O, m*n, since each cell is processed exactly once. Furthermore, this approach scales well for larger matrices, unlike the brute force method, which becomes prohibitively slow. While the dynamic programming approach is equally efficient, BFS is generally more flexible for grid traversal problems, and it's easier to adapt to variations of the problem. The brute force method, although conceptually simple, is not practical due to its excessive runtime. By leveraging multi-source BFS, we achieve an optimal solution that is both efficient and intuitive to implement. The problem we're tackling here is LeetCode number 542, the O1 matrix problem. Our objective is to calculate the distance from each cell in a binary matrix to the nearest zero. The distance is measured using Manhattan distance, which is simply the sum of the absolute differences in row and column indices between two cells. To solve this efficiently, we leverage a breadth-first search, or BFS, approach. First, we validate the input to ensure the matrix isn't empty or null. If it is, we return an empty matrix as the result. Next, we extract the dimensions of the matrix M4 rows and N4 columns. After that, we initialize the result matrix, called dist, which has the same dimensions as the input. Initially, all cells are set to a very large value, such as infinity, since we don't yet know their distances to the nearest zero. At the same time, we set up a queue for our BFS traversal. This queue will hold the coordinates of all the zero cells in the matrix, as these will serve as the starting points for our multi-source BFS process. For the pre-processing step, we traverse the input matrix. Whenever we encounter a zero cell, we set its distance in the dist matrix to 0, since it's already at the nearest zero, and we add its coordinates to the BFS queue. On the other hand, for every one cell, we leave its distance as infinity for now. This distance will be updated during the BFS traversal. Now, we perform the multi-source BFS. To do this, we define the four possible movement directions up, down, left, and right using a direction array. As long as the queue is not empty, we remove a cell, represented as coordinates x, y, from the front of the queue. For this cell, we explore all four possible directions to calculate the new coordinates, denoted as nx, New York. If these new coordinates are within the matrix bounds and the current distance at dist nx New York is greater than the distance at dist x, y, plus 1, we update dist nx New York to this new shorter distance. We then add the new cell's coordinates to the queue for further processing. Once the BFS traversal completes, the dist matrix will have the shortest distance to the nearest zero for every cell in the matrix. This approach guarantees a time complexity of O, m*n, where m and n represent the matrix dimensions. Each cell is processed once during the BFS traversal, and for each cell, we check its four neighbors. This results in a total of O, for *m*n, operations, which simplifies to O, m*n. Space complexity is also O, m*n, as the dist matrix requires this much space, and the BFS queue can store up to O, m*n cells in the worst case. To implement this, we use two key data structures. First, a queue is used for the BFS process, ensuring cells are processed in layers, starting from the nearest 0 cells. Second, the dist matrix is updated to store the shortest distances to the nearest 0 as they are found. The algorithm is robust enough to handle edge cases, such as matrices that contain only zeros or only ones. For instance, a matrix with all zeros will result in an output identical to the input, while a matrix with all ones will return a result filled with infinity or equivalent large values, indicating no zeros are present to calculate distances. The algorithm also accommodates other edge cases, such as a single-cell matrix. For a 1x1 matrix, whether the cell is 0 or 1, the algorithm will correctly handle the output. For non-rectangular matrices, where the number of rows and columns differ, like 1xn or mx1 matrices, the BFS ensures correct processing without any issues. To understand the algorithm better, let's walk through an example. Consider the input matrix 0, 0, 0, 0, 1, 0, 1, 1, 1. First, we initialize the dist matrix to 0, 0, 0, 0, inf, 0, inf, 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 and we populate the queue with the coordinates of all 0 cells 0, 0, 0, 1, 0, 2, 1, 0, 1, 2. This pre-processing step sets the stage for the BFS traversal. During the BFS, we process cells layer by layer. For instance, dequeuing 0, 0 leads to no updates since its neighbors already have shorter distances. Dequeuing 0, 1 updates the distance at 1, 1 to 1 as it's one step away from the nearest 0. The BFS continues until the queue is empty, with distances updated layer by layer. After processing all cells, the BFS completes, and the final dist matrix is 0, 0, 0, 0, 1, 0, 1, 2, 1. This output shows the shortest distance from each cell in the input matrix to the nearest 0. Cells that were initially 0 remain unchanged, while the distances for 1 cells reflect the shortest path calculated during the BFS. The algorithm is efficient, leveraging the multi-source BFS to minimize redundant calculations, and ensures correctness even for edge cases like non-rectangular or single-cell matrices. This concludes the explanation of the algorithm, demonstrating how it effectively solves the O1 matrix problem. To solve the 0-1 matrix problem, we start by importing the D class from the collections module, which will help us implement a breadth-first search or BFS. Inside the update matrix function, we first determine the number of rows and columns in the input matrix. Then, we create a distances matrix where each cell is initially set to infinity. This is because we assume that the distance to the nearest 0 for every cell is unknown at the start. Next, we initialize a queue to handle our BFS traversal. We then iterate through all the cells in the input matrix. If a cell contains a 0, we update its distance in the distances matrix to 0 and add its coordinates to the queue. This ensures that all 0 cells are our starting points for the BFS. We also define a list of directions, which represent the possible moves, up, down, left, and right. These will help us traverse to neighboring cells during the BFS. Now, as long as the queue isn't empty, we continuously process the cells. For the cell at the front of the queue, we extract its row and column indices and explore all 4 possible directions. For each neighboring cell, we check if it's within bounds and whether its current distance can be updated to a smaller value by considering the cell we just processed. If the conditions are met, we update the neighboring cell's distance to be 1 more than the distance of the current cell. This represents moving 1 step further from the nearest 0. After updating the distance, we add the neighboring cell to the queue so that it can be processed in future iterations. This way, the BFS propagates outward from all 0 cells, updating distances in layers. Once the queue is empty and all cells have been processed, we return the distances matrix, which now contains the shortest distance from each cell to the nearest 0. This approach ensures that every cell is updated in the most efficient way, leveraging the BFS algorithm to handle the propagation of distances layer by layer. Here, we start by defining the structure of our solution. We import the necessary packages and set up the update matrix method, which takes a 2D matrix mat as input. First, we determine the number of rows and columns in the matrix. Then, we create a distances matrix of the same size, initialized with integer.max_value, which represents the maximum possible distance. This step ensures that we start with the assumption that all cells are infinitely far from the nearest zero. Next, we initialize a queue to facilitate the breadth-first search, or BFS, which we'll use to calculate the shortest distances. After that, we iterate through the matrix, and for every cell that contains a 0, we set its distance in the distances array to 0 and add its coordinates to the queue. This is because cells with 0 are already at their minimum distance to themselves. Finally, we define an array of directions representing the possible moves up, down, left, and right, which will help us explore neighboring cells during the BFS. The breadth-first search begins with a loop that continues as long as the queue is not empty. At each step, we pull the front cell from the queue to process it. We extract its row and column indices, which are stored in R and C. For each cell, we iterate through the 4 possible movement directions. By adding the direction offsets to the current cell's coordinates, we calculate the neighbor's row and column indices, NR and NC. Before updating the distance of the neighbor, we check 2 conditions: first, whether the neighbor is within the matrix boundaries, and second, whether the current path provides a shorter distance than the one already recorded in the distances array. If both conditions are true, we update the neighbor's distance to be 1 more than the current cell's distance and add the neighbor's coordinates to the queue for further processing. This ensures that all cells are explored in the correct order of increasing distance. Once the BFS is complete, the distances matrix, now updated with the shortest distances from each cell to the nearest 0, is returned as the result. To solve the 0-1 matrix problem, we start with a small example. The input matrix is a 3x3 grid, where zeros represent cells that already have a distance of 0 and ones represent cells whose distance to the nearest 0 needs to be calculated. First, we initialize the number of rows and columns as 3. Next, we create a distances matrix, where all values are initially set to infinity. This matrix will eventually store the shortest distance of each cell from the nearest 0. The reason for initializing with infinity is to indicate that no distances have been computed yet. Next, we identify all cells in the matrix that already contain a 0. These cells are added to a queue because they serve as starting points for our breadth-first search, BFS. At the same time, we update their corresponding distances in the distances matrix to 0, as these cells are already at a distance of 0 from themselves. For this example, the cells at positions 0, 0, 0, 1, 0, 2, 1, 0, and 1, 2 are added to the queue. The BFS process then begins. We dequeue the first cell, 0, 0, and check its neighbors. Since all of its neighbors are either zeros or already processed, no changes are made. Similarly, for the next cell, 0, 1, we find that one of its neighbors, 1, 1, is updated because it previously had an infinite distance. The updated distances matrix reflects this change, and the cell, 1, 1, is added to the queue for further processing. The BFS continues iteratively until all cells have been processed. Each time we dequeue a cell, we check its neighbors. If a neighbor can be updated with a shorter distance, we update the distances matrix and add that neighbor to the queue. This ensures that distances are updated in the correct order, layer by layer, outward from the zeros. Once all cells have been processed, the final distances matrix for this example is complete. It shows the shortest distance of each cell from the nearest 0, with values propagating outward in a consistent manner. At the end of the process, the output matrix is 0, 0, 0, 0, 1, 0, 1, 2, 1. Now consider a larger and slightly more complex input matrix. In this case, the matrix is still 3x3, but the zeros are positioned more strategically at 0, 0, and 2, 2. We begin by initializing the distances matrix to infinity, similar to the previous example. However, the cells containing zeros are immediately added to the queue, and their distances are set to 0. These zeros serve as the starting points for BFS. During the BFS process, we dequeue one cell at a time and examine its neighbors. If a neighbor's current distance is greater than the potential new distance, we update it and enqueue that neighbor. This process continues until no more updates are possible. The final output matrix for this example is 0, 1, 2, 1, 2, 1, 2, 1, 0. For an edge case where the input matrix contains only zeros, the execution is straightforward. Since all cells already have a distance of 0, there is no need to perform BFS or any updates. The distances matrix remains the same as the input matrix. This demonstrates the efficiency of the algorithm, as it quickly identifies when no further computation is necessary. The output matrix in this case is 0, 0, 0, 0. In summary, the solution uses breadth-first search to calculate the shortest distance for each cell. By initializing all distances to infinity and starting from cells with zeros, we ensure that the calculations are efficient and accurate. Each cell is processed only once as its distance is finalized, making the algorithm efficient with a time complexity of O(m*n). Additionally, edge cases such as matrices with all zeros or all ones are handled seamlessly, demonstrating the robustness of the approach. To analyze the time complexity of this solution, let's break it down into 3 main steps. First, we initialize the distances matrix, which requires traversing the entire matrix to set up its dimensions of rows x calls. This takes rows * calls time. Next, we loop through the input matrix to identify all cells containing 0 and add them to the queue. This step also processes every cell in the matrix and therefore takes another rows * calls time. Finally, the breadth-first search, or BFS, processes each cell in the matrix at most once. Since each cell has up to 4 neighbors, the BFS operations are proportional to the number of edges in the graph, where the graph has rows * calls nodes and at most 4 * rows * calls edges. As a result, the BFS traversal also runs in rows * calls time. Adding these steps together, the total time complexity of the solution becomes rows * calls. Now, let's evaluate the space complexity. The primary contributors are the distances matrix, the BFS queue, and a few auxiliary variables. The distances matrix, with dimensions rows x calls, takes rows * calls space to store. The queue, which is used to manage cells during BFS, can hold up to rows * calls elements in the worst case, requiring rows * calls space as well. Lastly, variables such as rows, calls, directions, and loop iterators contribute only a constant amount of space, or O1. Combining these factors, the total space complexity of the solution is dominated by the distances matrix and the queue, resulting in rows * calls. When we compare this optimized approach to a brute force method, the efficiency becomes clear. In a brute force approach, for each cell with value 1, we would calculate the distance to the nearest 0 by traversing the entire matrix. With rows * calls cells, this would result in a time complexity of rows * calls, rows * calls, or rows * calls, 2, while the space complexity would remain 1. In contrast, the current solution leverages BFS to process all 0 cells simultaneously, updating distances efficiently. This brings the time complexity down to rows * calls, and the space complexity to rows * calls. Breaking it down further, in the best case where all cells are 0, BFS completes immediately with minimal exploration, achieving a time complexity of rows * calls, and space complexity of rows * calls. For an average case with a random distribution of 0 and 1, or the worst case where all cells are 1 except 1 0, the time and space complexities remain rows * calls, demonstrating the robustness of the approach. Finally, let's validate the big O notation mathematically. The total number of nodes in the matrix is rows * calls, and BFS ensures each node is visited exactly once. During this traversal, operations such as enqueuing, dequeuing, and updating distances are performed in constant time, or O1, for each node. Consequently, the total time complexity of BFS is proportional to the number of nodes, resulting in rows * calls. Similarly, the space complexity arises from storing the distances matrix, which is rows * calls, and the BFS queue, which at most holds rows * calls elements. Combined, these confirm that the overall space complexity of the solution is also rows * calls, aligning perfectly with our earlier analysis. When solving the 0-1 matrix problem, there are a few common mistakes to watch out for. First, confusing breadth-first search, or BFS, with depth-first search, or DFS, can lead to incorrect results. BFS is the appropriate choice here because it processes nodes level by level, ensuring that distances to the nearest 0 are calculated in the shortest possible way. DFS, on the other hand, doesn't process neighbors in an optimal order, which can result in revisits and inefficiencies. Another frequent mistake is failing to initialize distances correctly. The distance for cells containing zeros should always start at 0 since these are the source points for the BFS. Initializing everything to infinity or -1 without handling zeros properly can cause logic errors. Additionally, inefficient updates during BFS or dynamic programming are common. For BFS, not tracking visited cells or over-enqueuing already processed nodes can unnecessarily balloon the time complexity to O(n cubed). For dynamic programming, failing to optimize distance calculations during the forward and backward passes can lead to redundant computations. Lastly, it's critical to handle edge cases carefully. Examples include matrices that consist entirely of ones or zeros, single row or single column matrices, and non-square matrices. These scenarios require explicit testing to ensure your solution handles them robustly. Another mistake to avoid is relying on a naive brute force approach. While iterating through all cells and calculating the distance to the nearest zero for each might seem straightforward, this results in an O(n cubed) time complexity, which becomes infeasible for larger matrices. To approach this problem optimally, it's useful to highlight the intuition behind multisource BFS. By treating all zeros as sources and performing a single BFS traversal layer by layer, you avoid revisiting cells unnecessarily, ensuring an efficient solution. Alternatively, the two-pass dynamic programming approach can also be leveraged. Here, you propagate distances in one direction, such as top left to bottom right, and then in the reverse direction. This ensures that all cells have accurate minimum distances without redundant calculations. During interviews, it's important to ask clarifying questions about the input, such as matrix size and whether a zero is guaranteed to exist. You should also demonstrate how your solution handles edge cases to show your attention to detail. Finally, be ready to discuss the trade-offs between BFS and dynamic programming. BFS requires additional space for the queue, while the two-pass DP method is more space-efficient but demands a careful implementation. If you're looking to deepen your understanding of grid-based problems, there are several related problems that you can explore. Problem number 286, Walls and Gates, uses a similar multisource BFS approach. Here, the goal is to propagate distances from gates to all empty cells. Another problem, number 994, Rotting Oranges, also involves spreading an effect, this time simulating the rotting process from multiple starting points. For a more challenging variant, consider problem number 317, Shortest Distance from All Buildings. This problem requires BFS to calculate distances from multiple sources, and it adds the complexity of ensuring accessibility to all buildings. Finally, problem number 1293, Shortest Path in a Grid with Obstacles Elimination, takes grid traversal a step further by introducing constraints on how many obstacles can be removed. These problems not only reinforce BFS but also introduce variations that test optimization and edge case handling, making them excellent practice for interviews. To wrap up, let's compare the alternative approaches and their trade-offs for solving the 0-1 matrix problem. Multisource BFS is often the optimal choice for its simplicity and clarity. It has a time complexity of O(n*(m) and a space complexity of O(n*(m), as it requires space for both the queue and the visited matrix. The trade-off here is the additional memory usage due to the queue. On the other hand, the two-pass dynamic programming approach offers the same time complexity, O(n*(m), but is more space-efficient, requiring no extra space beyond the input matrix. However, it's harder to implement and demands careful propagation of distances in both directions, top left to bottom right and then bottom right to top left. Lastly, there's the brute force method, which has a time complexity of O(n cubed and a space complexity of O(1). While it's simple to implement, it's highly inefficient for larger matrices and is best used only for small inputs or as a learning step to understand the problem. By evaluating these approaches, you can choose the one that best balances efficiency and implementation complexity for the given scenario. To summarize, we solved the 0-1 matrix problem using an efficient BFS approach, achieving a time complexity of O(m*(n). Key takeaways include the effectiveness of BFS for shortest path problems and the importance of mastering grid traversal techniques. Thanks for watching, and be sure to like, subscribe, and share for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!